I think we are at
now live on
2:30.
YouTube, madam.
Perfect.
Let's give a minute or two.
Get ready to start the recording. And once I say record, you can start recording. Yes, we can get started.
Yes, please. Thank you.
Yeah. So Kishore, can you start recording? Good afternoon, all. This is our second industry assisted lecture series. The topic for this series is AI for IoT, and it is going to be conducted by IBM Research Labs. The first series, we did a 5-session series on electric vehicles. It was conducted in the month of August, and it went till the first week of September. We have the merit certificate, the completion certificate, and the participation certificate. All those have been uploaded in the portal. So those of you who have attended those series, you can probably get in touch with your coordinators and download your certificates for that session. For the session for today, I would welcome Dr. Kamal Das from IBM and Mr. Arindam Jati, who is the speaker for the day. I also extend my welcome to the PALS champions, Dr. Kelita Cherian and CN Chandrasekharan from PALS side. Kishore from the PALS Program Management Office, and my name is Sujata Sundaresan. We both are from the Program Management Office. We will assist you. I'll be the moderator of the session, and Kishore and myself will assist you through the session for any other operational or logistic details. Before I hand over the session to CN Chandrasekharan sir, I would like to show you a brief code of conduct. Just give me a second. Yeah, just give me a second. Yeah, I hope my screen is shown now.
Yeah.
Yes.
Yeah, so we are going to have 3 sessions. The first session, I did tell you that we will be having it by Mr. Arindam sir. A little discipline will help us in making sure that the effectiveness of this program, the reach is maximum. So what you need to do is, as soon as you log in, try to rename your Zoom name, include your college short name. It will help us to know that which college are you from, and it will also help us to connect back if there are any more queries or anything follow on that we need to do. We will know where to contact you. What will happen right now is, we will not allow any of you to unmute yourself. We would like the entire space to be given to the speaker. That doesn't mean that, there is no interaction at all. There are various means through which you can interact. One way is to raise your hand, get yourself unmuted, and then, ask your questions. The other way is to write a mail to Ask PALS PMO. Please note this, Kishore will be constantly posting this mail ID in the chat box all the time. So it is askpalspmo@gmail.com. Now, why do we ask you to write to the mail ID and not use the chat boxes? We will keep the chat box disabled. We will open it up only on request by the speaker. It is more to have an uninterrupted speech and nothing else. So if it doesn't mean that there should not be any interaction, you're always welcome to raise your hand or write your mail to this particular mail ID. We will be able to get your questions answered. There is an attendance link that we are posting. So make sure to post your mark your attendance and close the session as soon as you mark your attendance. Every time you keep the session open, it is going to be treated as one live connection, and that will affect our concurrent use on the portal. So as soon as you are marking your attendance, please close your session, the active session. And there will be a Slido quiz at some point in time during the session whenever the speaker prompts me to do that. So registration for Slido, again, we need to put an email ID and register for the Slido. Don't take your time at the time of the quiz. The registration for a link for the Slido will also be pasted by Kishore. Make sure that you register and be ready. The other things like, the feedback link, recording, all of those will be shared by mail post the session. So I hope the discipline or whatever we have tried to put in is clear and there are no questions on that. I would request Mr. C.N. Chandrasekharan, the PALS champion, to right now give a brief overview of PALS and set a context and get this session started. Over to you, CNC.
Thank you, Sujata. Good afternoon, Dr. Kamal Das, Dr. Anindam, and all others from PALS Partner Institutes. Little bit about PALS. Many of you might know this, but just let me just set the context for PALS and also for this session. PALS is a voluntary initiative of IIT alumni. We got together about 13, 14 years back, and we thought, what can we do to enhance the learning of students from engineering colleges are aligned to industry. So we thought a strong industry connection to their learning, learning by doing, learning by seeing, learning by mistakes. This kind of thing will help. It's also learning with NEP. So we talked to various industry, but the way it began is with a set of lecture series, just like we have now. But we have modified the lecture series into more robust ones. We started lecture series and we added a lot of programs to connect with industry for practical hands-on work, innovation, problem solving, and so on and so forth. So today we have about 22 offerings, one of which is this industry-assisted learning. So PALS has been continuously improving or enhancing the offerings that they started initially early on. So the offerings basket have been we have been going through what you're doing, how we can improve, etc., etc. So last year, like Dr. Kamal Das mentioned around April this year, but last academic year, we had requested IBM for a few sessions on emerging technology. And from IBM Research Lab, IBM India Research Lab, we got connected, fortunately, to Dr. Kamal Das and his colleague, and they did sessions. So in the past, our lecture programs have been standalone one-off programs, and they would be deep technology, emerging technology. We would leave it there and let the students and faculty, do further reading and understanding of that. Then actually later on, we all talked to Krishnakant Naik, who is not here, but he's been our IBM relationship manager, and spoke to Sujata and few others in PALS. Is it enough that we just do one session for students to pick up the concepts and the emerging technology, what is involved in that? Can we do a little more? Then we connected with Krishnakant Naik and said, can we do this? By all means, the IBM Research India staff, they would be willing to share their continuous work that they're doing on emerging technology, the emerging technology as they're applied in the industry. We thought that would be relevant. So just not stop at just one session. And if you see, the number of people joining is quite a large number today. Just now we have 450. We may hit close to about 900 to 1,000 as we go on. And recently, the session that Sujata called out, a similar series on EV was well received by students, and the students want more. So, Dr. Kamal Das, this is what I want to tell you that, you set the stage for this session, that you would have a series of talks by IBM India research experts to talk on the technology, how they are applied. I am not an expert, but we have expert, and I will now introduce the expert who is going to talk on this technology. Okay. So today we have the first of the series on AI for IoT. And today we have Dr. Anindam Jati, who is a staff research scientist at IBM Research India. His current research focuses on developing cutting-edge AI models for Industry 4.0 applications, with a specific emphasis on constructing foundational models for multivariate time series data. And Anindam earned his PhD from University of Southern California, USA. Prior to joining IBM, he worked at Microsoft Research, Washington, and Sony Interactive Entertainment in California. We are fortunate to have you, Dr. Anindam, for this session. And, I'm sure the students will benefit from what you are going to share today. Over to you.
Thank you so much, CNC sir. A good afternoon, everyone. So I'm going to share my screen. Okay, so my screen is visible.
Yes, sir. It is visible.
Yes. Okay, so today the topic of discussion is AI for IoT, and the basics I will mostly cover in this talk. And AI is kind of a term which is becoming more and more familiar to everyone. It's artificial intelligence, and IoT stands for Internet of Things. So here is the brief agenda. So we'll start with a term called Industry 4.0. And this is a term that is becoming very important in kind of now everyday applications of ML and AI. So I will explain what it means, Industry 4.0. Then we will go through how IoT data looks like, and what are the different AI and ML. ML stands for machine learning tasks that can be done on IoT data. And they will include multiple tasks, and we'll mostly focus on forecasting, classification, anomaly detection, regression, this type of tasks, which are mostly done on IoT sensor data. Then we will focus on more cutting edge technologies that are done in this space to work on this IoT data, which includes deep learning based methods. So I will give a brief recap on deep learning. And then we will pick one particular case study out of these 4 or 5 applications we have. And that will be a multivariate forecasting with deep neural networks. And then we will dive on a few state-of-the-art, very recent foundation models for time series. And then we'll have a hands-on session. So this Industry 4.0, I mean, this journey started long time ago. So we should know what is the first industrial revolution. So 4.0 stands for the fourth industrial revolution. And the first one started in the 18th century in Europe and United States. And it started with the breakthrough technology of steam and water power. And so before that, most of the industries were kind of handmade or animal-driven productions. But after this water and steam power, everything kind of started shifting towards machine-driven productions. And it affected all industries like textile, iron, agriculture, mining, etc. So the next industrial revolution happened around 1850. And it started due to the installation of many railroads, the innovation of the telegraph networks, and use of the oil and gas as electric power. And this created a huge benefit in the production line. It made the production very efficient. And as you can imagine, this affected all industries. All industries got benefited from this invention. And I think you can guess that the third industrial revolution started with the digital revolution. And it started in the late 20th century, like 1970, 1980. And so this started with the invention of digital computing, digital storage, and let's say digital embedded systems. So these embedded programmable logic controllers, or PLCs, were invented, and it created so this industry started using digital computers for record keeping. That even continues today. So it was a huge revolution. It's still going on, but we are kind of towards shifting to the fourth industrial revolution, which is basically this industry 4.0. And it has many factors. AI and machine learning is just the computing or algorithmic part of it. But in general, this industry 4.0 is possible if we have everything which we have in these 5 points, even beyond these 5 points. So, for example, in the Internet of Things, or IoT, which stands for or which encompasses all the sensor data. So these sensors are necessary to capture the data, and this data needs to be stored, and the AI or ML models that we have, that needs to be computed on the cloud. So cloud computing is also very important. And sometimes the AI models needs to be evaluated, or needs to be even trained on the edge. On the edge means on the device itself. So that is, those devices are generally very low in memory, and they have lots of constraints. So edge computing is also very important. And definitely cybersecurity is also a part of this industry 4.0 revolution. So our focus today will be on this, how AI models are generally used in very recent very recent technologies and very recent deep learning models. Will describe how they can be applied on IoT data for different type of tasks. So just to get a flavor of how industry 4.0 works, I will give you one example. So this example is from a software called IBM Maximo Application Suite. And I will play the video, which is available in the website. And let's all listen to it. So it will give a kind of idea why industry 4.0 is very important, and how AI models can be applied there efficiently.
The equipment you rely on to operate at peak operational performance and meet increased customer demands is more complex than ever. So when it comes to asset management, how can you lower costs without compromising safety or performance? You evolve your operating model with the IBM Maximo Application Suite, an integrated solution that delivers asset monitoring, maintenance, and reliability on a single platform, built on 30 years of market-leading Maximo performance to enable intelligence-based asset management that saves time, cuts cost, and optimizes performance. Let's say Alice is an operations analyst with your company, and she's using IBM Maximo to remotely monitor all of her company's assets in a single view. The AI alerts her that there's an issue that warrants immediate action. With a click, she can see she can drill down to investigate. The issue requires a physical inspection, so she creates a service request. And since everyone on Alice's team has access to IBM Maximo, which also integrates all data and workflows together, the second Alice completes and submits her request, Franklin, a maintenance supervisor, receives a work order. Franklin evaluates assets across multiple facilities from a central location. He reviews the work order and attaches the appropriate job plan from Maximo's rich industry-specific workflows. Then Sarah, a technician chosen for her expertise in this area, receives notification of the work order on her mobile device. Sarah pulls up the asset's history, job plan, and documentation, and she gets to work. The fix is one she hasn't done before, but Sarah has 2 options to assist her in completing the task. She can use prescriptive AI assistance that analyzes, provide the fix with the highest probability to succeed. Or she can contact an expert remotely for support. Here, she's using the camera on her tablet to show her colleague the asset in need of repair. She also uses the camera on her tablet to receive visualized step-by-step instructions delivered in real time. Once she makes the necessary repair, the actions taken are logged in your maintenance history. The new data then updates the asset history, and a recording is stored and available for the next person who has this issue, creating a continuous learning loop, ensuring you have better AI-driven insights into all facets of your operations, including the health of your assets, better predict failures, utilize AI-powered vision models, and optimize service scheduling, as well as worker safety, all on a single platform with multi-cloud deployment options. Host IBM Maximo in the environment of your choice, or let IBM manage it for you. Transform your business with IBM Maximo Application Suite, the complete asset management package to keep your business thriving for years to come.
Okay, so I hope this kind of gives a flavor on how AI can be very useful in asset management, which is one of the most important requirement in Industry 4.0. And you saw that AI-driven models can do predictive maintenance, which is extremely important because you can, from the historical data, you can predict whether there will be a failure or whether the system is going to a bad state. So you can take maintenance ahead. So now I will move to IoT data. And so it stands for Internet of Things. And this IoT data is nowadays everywhere. So let's say starting from the home automation like voice assistants or elder care, in healthcare, in smart traffic control, for example, the automatic speed monitoring systems, and industrial manufacturing for asset management, for agriculture, environment monitoring. Everywhere, AI like IoT sensors can be installed, and nowadays it's almost everywhere. We might not know. Now, one thing is that there is a misnomer of internet. So when we say Internet of Things, that doesn't mean that the sensor needs to be connected to the public internet. A group of sensors can be connected to a let's say private network. So the criteria is that these sensors should have an IP address so that they can be individually accessed. And then this data is generally used for the subsequent modeling. So the focus of this session will be IoT sensor data, which is relevant in several Industry 4.0 applications. And so there are the sensors can have different types of data. It can capture images, for example. It can capture video, and it can capture the standard data, which is temporal. For example, in an industry, the sensors can capture the temperature continuously. Every minute, it can capture temperature, the pressure of the system, the humidity, the moisture, let's say the wind flow. So all these things they can capture. And when this type of data are captured by these sensors, they generally create a time series, because they are generally captured at a fixed interval, let's say every minute or every 10 seconds. So it creates a time series, and it's multivariate because there are multiple of sensors, each capturing one particular thing, pressure or temperature, like that. So our focus will be on this particular type of data, and then we will kind of focus on a particular case study. So let's say this is one typical multivariate IoT time series data. It looks like this, and I am showing one data. It's called electrical transformer data, and it's a publicly available data. That's why I'm showing it here. But generally, all the IoT sensor data from industry look like this. So you will have multiple of this time series, and let me take the laser pointer. So each of these is a time series. So x-axis is time and y-axis is value. And you can see here we have 7 time series with different colors. And so each one is a univariate time series. So basically, if we want to represent each time series, it's just an array. And but we want to represent multiple of them. And all of them or some of them might be important for us. So one important aspect of multivariate time series is that they might have inter-channel correlations. So when I say channel, I mean, so every channel is one univariate time series. So in this case, we have 7 channels. And so because let's say this OT, this is the oil temperature of an electrical transformer. And this OT might be dependent on some other variables, which are also captured through some IoT sensor. And so they have correlation with each other. If this blue curve increases, maybe this pink curve also increases. That means they have some correlation or interdependency between them. So that basically means, if I go back, so whatever model we want to train on this type of data, it should capture these inter-channel correlations if there exists something like that. So some of the kind of names or nomenclature that we will use. The channel I have already described. So in this example, I have a 2-variate time series. So it has 2 channels. And when we talk about dimensionality, so it basically tells about how many channels we have. So it's a dimensionality of 2. And when we say length, that means what is the entire length of the time series. So just to have an idea how big this data can be. So in some of the industries, you might see data for 10 years. And so last 10 years data, let's say 2010 to 2020, you get 10 years of data, and you can have thousands of sensors. So let's say 2000 sensors and 10 years of data, and you're sampling this. So this vertical lines are basically the sampling time points, right? And so this sampling time points can be, let's say, every minute or every 10 seconds. So just imagine if I have a 10 seconds interval time series data for 10 years with 2000 channels, how big it will be. So that type of scalability the model has to achieve, whatever model we build for a particular downstream task. Okay, so so here is a mini quiz. So we'll have just little questions just to explore if we are learning the concepts properly. So Sujata, can you open the chat box for now? So the question is, so we have yes. So we have seen this multivariate time series data, which has channels and which has time length. So the question is, what data structure is suitable for a multivariate time series?
The chat box is open.
Yeah. So if it's on top of your mind, just type that in the chat box. Okay, so the question, just to understand the question, so I got 2 answers, but those are mostly models. So my question is, what data structure is suitable to store the data of a multivariate time series? By data structure, I mean simple, just try to recall in C language what type of data structure you have read, right? Array or list or whatever, right? Okay, so I got one answer I can see, so we can close the chat box for now. So I got one answer, 2D array, and I got lots of answers. So yeah, some of them might also make sense. So I got array, I got 2D array, I got tree, I got list. So yeah, multiple of them are correct. So let's say 2D array is the thing, because I have, let's say, so one of my dimension is channels. So let's say I have 7 channels, and another dimension is time, right? So we have to store all the data. So it's a 2D array, but list is also correct answer because I can have a list of lists. So, so I can have 7 lists and each list containing all the data. So list of list is also an correct answer. And some other complicated data structures can also be used, but let's focus on the simple one. Right. So here is a, so we can use pandas. So if you are familiar with Python, pandas is a very useful package library, open source library that is used everywhere and very extensively in industries. So I would request, if you are not familiar with pandas, so get familiar with pandas. It's very important and it's used everywhere in industries. And so let's say I have my data in this in a CSV file. For larger data set, it can be some other file type. And then I load the data and display in pandas. And you can see in pandas, it looks like a 2D array only. So I have time axis, and which is in this y-axis, and my x-axis, I have these channels, which are, let's say, 7 channels. And sometimes we also have date and time associated with the time series data. If we have that, that's good. We have more information. Sometimes we might not have that. It's just sometimes in industries, people just give you, let's say 7 cross whatever time, 17,000. This array will be given to you. So this is how the data looks like. And yeah, so we will explore the other part later, modeling part. Okay, now, so now let's discuss what are the very important AI and ML tasks on multivariate time series data. So probably the most important task, arguably I would say, is multivariate forecasting. Because whatever you want to do with time series data, particularly from an industry 4.0 perspective, you want to do it in advance. So if you want to detect a failure, there is no point in detecting a failure which has already happened. So you want to detect a failure way ahead of time. Sometimes you might be asked to detect a failure 1 or 2 hours ahead of time, right? So forecasting is something which might be one of the most important tasks in multivariate time series. And so forecasting basically means predicting the time series in future, right? And so let's say it sounds probably a little difficult in the sense that how can we predict the future? But the idea is that generally time series have patterns and they have correlations among them. So let's say if there is some pattern in the time series which repeats again and again due to some factor which is also in other time series, then probably it will be able to forecast the time series way ahead of time. And I will give specific examples of how it is possible. But let's look at the same time series, which has 7 channels. And there are different types of forecasting. So the first, this is the type 1, when we want to forecast all the channels. So given this historical data, it can be even longer than what it is shown here. So you want to predict the forecast. So let's say this is a minutely data. So every minute the data is captured. Let's say given 70 minutes of history, you want to forecast 25 minutes of in the future. So something like that. And in this particular example, you want to forecast all the channels. So some of the examples are let's say weather forecasting. So you have, let's say, temperature, humidity, etc. You want to forecast everything. So that is like forecasting all the channels. Second type of application that comes often in the industry is forecasting only a few channels of importance. And these channels are called target variables because they are the target variables. We are kind of forecasting them. So let's say in this particular example, let's say the top 2 channels are of importance. So we want to only forecast these 2 channels, and we don't want the forecast of the other channels. But we can use the history of the other channels to forecast these two channels. So in the history, we can use everything, but we only care about forecasting these two channels, these two target variables. This often comes in the sense that, let's say you have a specific manufacturing system where you have lots of sensor installed, but what you care about is, let's say, some particular key performance index of the business process. Let's say you are manufacturing some metal, and what you want to mostly forecast is what's the consistency of that metal. So that is only your KPI, key performance index. And so, or you want to forecast only some state variable of the system, which kind of mainly manages or mainly maintains the goodness of the system. So you only want to forecast that and see whether your system is good or whether or it's going to a very bad condition in the future. So in this case, when we are not using the other 5 variables, we sometimes call them as conditional variables, in the sense that this forecast of these target variables are conditioned on these conditional variables. And also note that you can use the history of the target variables. You can always use that. There is no harm in using that. And you can also use the history of the other conditional variables. And the third type of multivariate forecasting, it is also something that often comes in the industrial requirements. So here you want to forecast only these 2 target variables, but some of the other variables are also available in future. So this let's say this orange one and the purple one, I am showing that these 2 are also available in future, and they are generally called exogenous variables with future available, or sometimes they are called control variables. So I will say why and how it can be possible. Let's say you are kind of this is a manufacturing system, and there is something for the operator to control. And the operator controls this purple and this orange time series and set the value to some value at this particular current time. So this vertical line is the current time. So at this point of time, the operator sets the value to something that this will go down and up and go down and up. So like this, it's automated in that way, right? And based on that control variable, so that this control variable or this exogenous variable, this is available in the future. So for the next 4 hours, I set my control variable in this way. And based on the control, the target variable or the KPI, whatever we have, is maintained. So during modeling, if we have some control value that is already available in the future, we can leverage that. We can use that also in our modeling to produce a better forecast of the target variable. So these are the 3 main types of multivariate forecasting. At type 3 actually is the superset. It encompasses all we have seen in the other 2 types, type 1 and type 2. Okay, so this is something, I'm not opening this for chat, we'll just discuss here. So this is something, let's say this manufacturing system I just talked about. So we have multiple sensors installed, let's say temperature, pressure, moisture. These are sensors which are capturing all this data from your entire manufacturing system. And based on the raw materials and based on the wind flow, the output is kind of you are getting from the system. And so this raw material, the operator is kind of providing to the manufacturing system. And also there is something called, let's say, wind flow, which is also important in some of the manufacturing systems. And this wind flow, the operator can control. So they can say, okay, I will have this wind flow value or air flow value at this level for the next 4 hours. to get a particular output at this rate or at this consistency. So this wind flow can be used as a control variable or exogenous variable with future available. Okay. So we'll move to the, let's say, some other tasks which are useful for multivariate time series. So some, apart from forecasting, one major task is classification. So this is very important in, let's say, healthcare, in the sense that, let's say, you have EEG or ECG time series collected, and you want to classify whether a particular time series it's a normal heartbeat like this yellow one, or it has some abnormality. So it's a classification. So given the entire time series, you just need to say whether it's a binary classification. So you need to say whether it's a normal heartbeat or it's a abnormal heartbeat. So like that. So there is a this repository available for time series classification, and there is also some data sets in the UCI, which you can use, download, and try your classifier for time series classification. And another important task for time series is anomaly detection. And so this is something extremely important, because for asset management, because we want to see whether something will go wrong. And generally, it has to be done in a completely unsupervised way. There might be some supervised data from the past. So when I say unsupervised, means there is no manual label from the data that, okay, this particular time series is anomalous and this is normal. Generally, there are lots of unsupervised techniques to detect anomaly from the time series. And this is mostly important when we can detect the anomalies in the future. So this is also related to forecasting. So both a forecasting model and anomaly detection models are sometimes used together to perform this task. And also another task is time series regression. So in this case, this is kind of similar to forecasting. But the thing is that there is a completely different regressor value. So for example, here are two time series. So it's a two-variate time series. Let's say humidity and temperature you are collecting inside a particular room. And given a historical data, let's say last 1 hour of data, or you want to just predict the power consumption of the house. So this power consumption is somehow related to the temperature. If the temperature is high, people will use more fans or AC, so power consumption will be high. So from this given time series, you want to regress something. So you can regress one thing, you can regress multiple of them, but in general, this is what time series regression problem will look like. And there are lots of data in the time series regression problems data in UCI repository. So you can also have a look at this data. So our case study will be multivariate time series forecasting. So we'll start with some basics of forecasting, and these basics are extremely important to understand, so that because they will be helpful in understanding the very cutting edge deep learning based technology in forecasting. So these are all univariate things, but these concepts are also can also be extended to multivariate time series. And I'm referring, so all this like in the next few slides, whatever we have this for forecasting basics are from this book by Professor Hindman. And this book is freely available in the internet. Okay, so this is something, let's say, Sujata, maybe can you open the chat box once more? So this is something we want to explore or brainstorm. Let's say if I have this time series, this is some time series I took from this book. It's called Australian Anti-Diabetic Drug Cells. And you see there is a time series for a few years. And the question is, what are the major characteristics of the time series? What do you see from this time series, right? So why do you think this can be forecasted? Right, so let's see the answers.
The chat box is open.
Yeah, I think I got some correct answer already. So we can close it for now. Yeah, so you can also see the answers, right? So there is repetitive pattern, there is cycles, there is steps, there is seasonality, there is trends. So yeah, all of them are right answers. So you can clearly see there is this repeating patterns. That means this is something that will come again and again. So even with a very easy modeling, you can model or you can forecast, you can say what will happen, something like this will happen, right? And you can also see there is a increasing thing. So this increasing trend in the time series. So we have particular terms for this in time series. So we call this seasonality. That means how often these repetitive patterns we see. So let's say it can have a quarterly seasonality. That means you see the things are getting repeated again in each quarter, like every 3 months. And there is a trend in the time series. That means the time series is eventually increasing. So this is happening because it can happen due to many reasons, right? So you can guess, right? This is anti-diabetic medicine cells, right? So maybe people are getting this diabetic nature. This pattern is repetitive due to some reason, due to some festival or some reason. And the trend is increasing because probably people are there is more people, number of people is increasing in a particular country. And also people are getting more aware that they need to get the medicines for diabetes. So this is also increasing. The overall value is also increasing. And you can see the amplitude of these peaks, they are also increasing, right? So this is a pretty easy time series to forecast, I would say. So there are few things we need to understand from basic time series concepts, which are very useful even for using deep learning for time series forecasting. So one thing is autocorrelation. So this is something which tells some important notions about the repetitive patterns of the time series. So this is something you can see. We take the YT, that means the current time. We subtract the mean value of the time series. This is just for normalization purpose. So if you just ignore this Y bar, minus Y bar from this term and this term, it's something basically YT multiplied by YT minus K. And there is a normalization factor in the denominator also. If you can just ignore that, it's basically YT into YT minus K for a particular K, RK. So basically what you are doing, you are taking the time series, you are making different lags with K. And so basically you are shifting the time series and then calculating a correlation, a dot product. So you are seeing basically, let's say I take this time series, I shift it. So it will be something like this from here, and then I take a dot product. So that dot product will tell so how my previous observations are similar as the current observation, how YT is similar in nature with YT minus K. And this, if I plot this for all the values of K, so K I start from 0, 1, 2, 3 like this, then I plot it. So that is the autocorrelation function ACF. And this ACF is very important to know that because depending on the nature of the time series, your ACF will have different patterns. So I would ask you to read this Professor Heineman's book. So someone asked for the links, that just Google Professor Heineman time series book, it will come in the first link. To know more about autocorrelation, just read that chapter. So I will give one particular, let's say, brain teaser. So let's say I have a white noise. People have heard about white noise, right? So So the question is, maybe Sujata, we can open the chat box once more. So the question is, what is the autocorrelation for the white noise? Let's say how it will look like.
Chat box is open.
So question is, the autocorrelation for white noise, how it will look like. Okay, we got some correct answers already. So you can close it. So yeah, so zero is the correct answer. But if you just go back after this session in Python or MATLAB, you create a white noise and then try to plot the autocorrelation. You will probably not see exactly a 0. You will probably see something like some value, and that generally comes due to some random patterns in the white noise. So generally, when people plot the ACF, they also plot these blue dotted lines. So these blue dotted lines are something that is kind of insignificant. So even white noise can have autocorrelation, non-zero autocorrelation within these blue dotted lines. So if we have something beyond that, that's something kind of significant. So just read this chapter from the book. It's very well explained there. Okay, so the next concept, which is very important, is time series decomposition. And this is something, let's say, extremely important, I would say, even in modern deep learning techniques, sometimes use that. So what we want to do, given a time series, which is the first plot here, this is my time series. I want to decompose it into multiple factors. So first, I want to get the slow moving thing, which is the trend. Let's say I extract it somehow from this time series. Whatever remaining is basically the seasonal pattern and the noise, right? So this is something called which is called decomposition. And the first thing what we remove is basically the trend. And if I subtract the trend from the time series, I will get something which is seasonal plus random factor. So if I subtract the T, the trend, I will have S plus R. So this S plus R I will have. Then there are some ways to extract the seasonality factor. And the rest of the thing that is present is noise. And noise you cannot model with any modeling techniques. So basically, if you have these two things, trend and seasonal, there are lots of deep learning models also which decomposes the time series and then model them separately to get a better modeling accuracy for forecasting. So there is a classical way to do that. So let's say I can apply a smoothing filter, let's say moving average filter or something. If I just smooth this time series with the moving average filter, I will get the trend. Then I subtract that, then I try to get seasonal, etc. And there are lots of packages already available for you. So there is an open source repository called Stats Models. So if you just Google, you will find it. So Stats Model supports something called STL decomposition. This is a state-of-the-art, very standard decomposition technique. So people generally use this type of standard libraries to do the decomposition directly. Okay, so for further reading, I will ask everyone, if you are interested in time series, please read the basics from this book. And there are multiple things you should just know about them, even to understand deep learning models. So ARIMA, SARIMAX, and exponential smoothing, the STL decomposition. These things, if you are at least if you have the basic knowledge, it will be very easy to read the complicated deep learning papers. Okay, so now to kind of describe about deep learning, how deep learning can be used for forecasting, we'll have a quick recap of deep learning and machine learning. So as you know, there are different types of tasks. Let's say supervised task where we are given human labels. Let's say image classification is a supervised task. And there are unsupervised tasks where you have just a data no human levels is available. You just want to cluster the data and see what the major clusters are available. There is semi-supervised task also, and there is where you do not have, let's say, enough levels. You have some levels which are like labeled by humans, but there are lots of samples without any labels, and you are to train a model for classification. So that is something like semi-supervised class, semi-supervised problem. And there is also reinforcement learning, which is also very popular. So yeah, this quiz will just, I just described semi-supervised example. So let's check out some notations that we'll be using. So when you see something, let's say not bold, it's generally a scalar, unless there is a typo I made. So when there is something is bold but it's like small case, so that's a vector. And when there is a like large case bold, that means a matrix. So generally we denote the samples. So every sample for image classification, one image is a sample. So for time series task, one multivariate time series, that 2D matrix we saw in pandas, so that entire thing can be a sample. Or what we can do, we can create windows from that. If it's very long time series, if it's a two-year time series, we create multiple windows from the time series, and every window will become a sample. And there can be label, so it can be scalar or vector. For here I'm showing scalar. And then there is learnable weights. So these weights are model weights, let's say deep learning weights. These are which are learned during training. And model prediction is generally denoted with this hat. So yi hat means it's a prediction from the model for the ith sample. So let's take this example. So we have a ECG data, and it has 3 different channels. And so this is my sample. And I learned some model weights, and my model predicts one class, it's abnormal. Right. So this is some example of this. So for forecasting, let's just discuss this. So let's say I have, I want to take this and I want to forecast for 10 more points. So I want to forecast here, 10 points here, 10 points here, 10 points here for this three time series. And so in that case, my sample is this length, my input is this length cross 3. So here it will be 3. And then my label is basically what I have in my historical data. So I sample my input and my label from the historical data. So my label will also be, let's say, 10 points in time. So 10 cross 3, that will be my label. And in that way, I create multiple samples, X and Y pairs for training. So I will show this in the hands-on session, how we create this window and how we mine the samples from a time series to do the model training. Okay, so let's take a recap on deep learning. So I think the best way to start deep learning, if someone has not, let's say, yet started, is to start with linear regression. So let's say you have some data points like these blue dots, and you want to fit a curve there, right? The fitted curve is the blue line here, right? So generally, we call it linear regression because my model is linear. So my predictive model, which is y hat, this is some linear function of x. And this is W transpose X. That means basically, if I have, if X is a vector, my sample is also a vector. Let's say X1, X2, X3. So I just have W1, X1 plus W2, X2 plus W3, X3 plus B, the bias term. Right. So generally, the objective function is mean squared error, because whatever you want to fit, you want to reduce the squared error between the fitted model, fitted line, and the actual data. So you basically take the actual value, which is yi, and the predicted value of the model, which is yi hat. You take the squared error and sum them, average them over all the samples. So that is your mean squared error. And then y hat is basically this linear model, which I put here, right? So this is the linear regression, right? And this is very important. We'll see why to understand. So now we have some quiz questions. So Sujata, can you please open the chat?
I'll do that.
So first question is, what are the learnable parameters for a linear regression model? So I have written the objective function here, which we just saw. So which are the parameters of the model that we will learn when we train the model? So I get the first answer, W. So all W. See the equation once. There are three parameters, W, X, B, Y. Yeah, so I got W and B. Okay. So yeah, so the answer is W and B. So because B is also the bias term, which is also important. So both W and B are something that we will learn when we train a linear regression model. So the second question is, let's keep it open. So the second question is how to minimize the objective function. So it means yeah, it's probably you have to write something. Let's say you can write in very 1 or 2 words. So when I say how to minimize, it means when I minimize a function in basic, let's say 12th standard math, if we want to recall, what do we do when I minimize a function? Yes, so I got the answer, differentiation. So yeah, so I think it's the correct answer. So generally, when we minimize a function, we take the derivative and we make it 0, and we try to, let's say my learnable parameters are W and B. So we will find the derivative with respect to W first. So it's called a partial differentiation, and we'll make it 0 and find the optimal value of W. We'll do the same thing for B, and we'll find the optimal value of B. This is how we minimize a function. The same thing can be done here. Right. Now the next question is a true false question. So for this particular linear regression equation, is a closed form solution possible for this equation? Yes or no? Yes. So I get most of the answers yes. So now we can close the chat box for now. Yes, it's possible, because even you can try in your pen and paper that you can just try to take differentiation both with respect to W and B, you will get a closed form solution. So the thing is that, let's say if the closed form solution is not possible, or even if it's possible, can we use some technique to find the differentiation, find the optimal point? Right. So in most of the deep learning, multi-layer deep learning networks, this closed form solution is not possible with respect to all the parameters of the neural network. So people are mostly familiar with stochastic gradient descent. So people use SGD to do that. So SGD is very easy to understand if you just think about this plane curve, and if you drop a ball, where the ball will land. Mostly it will land in this global optima or global minima. Right, and this is the SGD equation. So we want to update the weights. Weights is the parameter that I'm training. So I need to, my next weight will be my current weight minus some learning rate multiplied by the gradient of the objective function at this point WT. And this J is the objective function. So basically we want to go in the direction opposite to the gradient. So if the gradient direction is this direction, we want to get to the we want to move to the opposite direction so that we reach the minima. So generally, this gradient descent is, I mean, it can be done on every sample individually. So let's say in your data, you have 10,000 samples or 1 lakh samples. So you can individually update this weight for every sample, or you can take all the samples and take an average gradient and then update the weight. So both of these are extreme things, and there are problems with both of the techniques. So either choosing one or choosing all. So people choose mini batches. So let's say I choose a particular mini batch size, and with that mini batch size, I calculate the gradient. I take the average gradient, and then I update the weight, and I keep doing that for all the mini batches until I am done with all the samples in the data. So when I'm done with all the samples with the data, then that is one epoch. So I'm done with one epoch of training. Then I can repeat again for multiple epochs. So generally, the question is, can SGD always guarantee global optima? And the answer is not, because let's say I have a objective function like this, and I start. So all the SGD starts with some random initialization of the weight. Maybe it's 0 or maybe some random value. So I will start somewhere. So I can start here, and then the ball can drop here and stay forever for here. So whether my global when my global optima is here, which has the most minimum value, but this ball will never reach the global optima. So this SGD cannot guarantee global optima. If it depends on the objective function. So if the function is convex, then it can reach the global optima. So this convexity is also something, a very important concept to understand. So you can see this this function is not convex, but this function is convex, right? And so this slide is from Wikipedia. So I think you can just go there later to understand the convexity concept. So now this SGD is the first basic optimizer algorithm. And now there are lots of concepts that came after SGD. So one concept is, this concept of momentum. So when you capture the exponentially weighted moving average of the gradient, and then instead of the gradient, you replace the gradient by this moving average value. So basically, you are giving a momentum to the learning equation, and that can be sometimes helpful for faster convergence. And so you can see in PyTorch, if you go, there are lots of other optimizers apart from SGD. Some of the popular ones are Adam and Ada Delta and these things. Okay. So now we'll slowly move to the neural networks, and the basic. So let's say if we understand this perceptron and linear regression and logistic regression, these things very well, the multi-layer perceptron or CNN or RNN or transformer, all these concepts become easier to understand. So let's say, for example, perceptron. Perceptron is a model that is used for binary classification. It has only one. You can imagine a neural network with only one layer, that is perceptron. So let's say I have these two types of samples. It's a binary classification task, blue and red. And so by learning a classifier actually means by learning a hyperplane. So hyperplane, when I say hyperplane, in 2D, it's basically a line. So when I train a classifier, I'm basically learning a set of weights, which basically denotes a line in that space. And in a multi-dimensional space, instead of 2D, if my sample is 100-dimensional sample, let's say one image, then this line is called a hyperplane. So let's say if this is a hyperplane I learn, this is not a good hyperplane, right? Because it cannot separate the two classes well. This is also not a good one. But this is the perfect one. This is the best hyperplane that I can learn here. So this is what generally we learn when we train a perceptron algorithm. And what perceptron does, it kind of creates the loss function in a way that if the predicted level matches the original level, it does nothing. But if there is a mismatch, it either moves the hyperplane towards this direction or towards the opposite direction. So it's a very simple, or the simplest SGD equation. So you can also try later in your laptop to do that, and for a simple binary classification task. So the next one is a logistic regression. This is also very important to understand because this sigmoid function is used in this logistic regression, which is also used in lots of neural network operations. So we have learned about linear equation when we had this WTX plus B equation. So this is a linear equation. When we add this sigmoid over this equation, it becomes a nonlinear function because this one is a nonlinear function. And this logistic regression, although it's called regression, it's basically a binary classification model. So you might have heard that this is trained with something called this binary cross entropy loss. And if you like read any textbook, you will see, or you can try it yourself. You try to take the derivative of this equation with respect to the model weight, and then just derive it. Then you will come to this equation, the SGD update equation. And you can also try, when you have this SGD update equation, you can try to build a logistic regression yourself in your laptop for a binary classification task. Okay, now, so from this perceptron logistic regression, from these concepts, now we have this big networks. So we have the multi-layer perceptron first, which is MLP. And so this MLP is basically multiple layers of perceptron you can imagine, but we have some non-linearity in between them. So let's say I have one layer here, then another. So the input goes to that layer, and then I have a ReLU activation, which is a non-linearity. Then I have another layer, then I have ReLU activation, which is again a non-linearity. So in this way, you can create a very deep neural network, which is called the multi-layer perceptron. So, one quick question. So I think what I'm seeing based on the time, let's discuss here without instead of opening the chat box. So the question is, what will happen if there is no ReLU activation in an MLP, right? So if I remove these two ReLU activation, what will happen? Like this, right? So essentially, you can imagine that. So if there is no nonlinearity at all, so this is becoming just a linear model. So because there is W1 and there is W2, there is W3, you can just multiply each of them. And W1 multiplied by W2 multiplied by W3, you can represent this multiplication as one matrix W. So it's just a linear model. So you need some nonlinearity to make it a nonlinear model, which is useful in complicated classification or regression tasks. There is also CNN. So I'm not describing these things in very detail because these are mostly available openly in online platforms. So CNNs, instead of learning just like multiple layers of perceptrons, we learn different kernels, and these are called convolutional kernels. And there are multiple layers of that, and multiple convolutional filters are there. And one by one, we stack them. And there are multiple other design choices. There is maximum pooling. There is dense layer at the end. So these are very useful for image processing tasks. Also, these have been useful for speech processing tasks as well, and time series processing tasks as well. There is recurrent neural network, and as the term says, it's mostly for recurrent tasks. So for time series tasks, it's very useful. But recurrent neural networks have issues in convergence. So even though it's very useful and very probably easy to model time series because it can model variable length time series very well, but if you see the state of the art modeling, you will see RNNs are not doing well because there is an issue in convergence. The issue generally happens due to vanishing gradient or exploding gradient, etc. There are other so the main issue is the vanishing or exploding gradient, and there are other techniques, other models, more sophisticated model like GRU or LSTM for like tackling these issues. I think the most popular model, I think everyone has heard of it by now, is the transformer model, and this came in a I think 5-6 years ago or 7-8 years ago, this attention is all you need paper. It came and this is one of the most revolutionary papers in this decade. And in almost every domain, people have adopted transformer models for solving tasks from computer vision to natural language processing, speech processing, and also in time series. So this paper, before reading this paper, if you have not gone through this Jay Alamers blog, so I would suggest this illustrated transformer blog. This is very easy to understand. So, but one caution is you should at least understand multi-layer perceptron and those concepts before you should jump onto transformers. Okay. So now we will recap some of the recent state-of-the-art works for using deep learning for forecasting. So, so I think this year, a few months ago, we have published a blog on time series foundation models. The title is The Battle of Time Series Transformers. So this is from our own team. And this is a blog in LinkedIn. So yeah, it's hard to get the link, but if you can take a screenshot, if you can, but you just Google search with this title, it will come in LinkedIn. And this is a very good blog. So I would suggest you to read because it has a very story-like reading flavor you will get, and it's very easy to understand what is happening in the latest technologies for multivariate time series. So I will just give a summary of this blog. So this is like last 4 years research I have summarized here, as these are all like state-of-the-art models that came in the last 4 years. And you can see these red things is all transformer. So all transformer models that are kind of the recent big models that are coming, they are becoming state-of-the-art, and another transformer model is kind of beating it. So this is going on. So I'll tell an interesting story. This is also in the blog. And you can see the name also. It's all informer, autoformer, fedformer, pyroformer. So all like transformer derived models. So the first, the very first model was model with transformer for time series was from UCSB, LogTrans. And after that, I mean, it was not used as a foundation model. So I will explain what is a foundation model. But IBM Research was one of the first team to publish this TST paper, which showed that foundation model is also possible for time series. So when I say foundation model, so we talked about different tasks in time series like classification, regression, forecasting. So the idea is that can I pre-train one model which can then be fine-tuned for multiple tasks like this regression, classification, and forecasting. This is similar to natural language processing, where people train, let's say, one big language model, and it can solve a lot of tasks. Like you can see ChatGPT solving different tasks like sentence completion, grammar checking, answering your questions. So multiple tasks are solved by ChatGPT. So similarly, we can have time series foundation model, which can be pre-trained once, and then it can be fine-tuned on multiple tasks. So this first idea came from IBM Research with this TST model. So this model, in general, the basic architecture is you take the time series transformer encoder and try to train the model with the time series. And there are different flavors of it. You can train it in a supervised way, or you can pre-train it as a foundation model way. So I'm not going through the detail of this thing. But if you see this, this journey, so you can see that, so there was LogTrans here, then all this transformer model came, right? TST, Informer, all this thing up to Triformer, and there might be more. And so then there is a disruptive technology that came last, I think this year. and it's called D-linear model. And the title of the paper was Are Transformers Effective? And for time series modeling. And this was a surprise findings because D-linear found that, so all these models you see here, 5, 6 models, D-linear was a very simple model. It's just it does time series decomposition. So that's why I said it's very important concept. And then it uses a very simple linear model with a properly tuned hyperparameters. And it shows that it can beat all of these prior transformer models. So you can see that these bold numbers. So there are multiple data sets on the left: electricity, traffic, weather. These are all different data sets. These are benchmark data sets. And you can see this D-linear is outperforming all the transformer-based models: fed-former, auto-former, informer. So the question was that then are transformers actually effective in modeling time series? So that kind of D-linear was a kind of raised that question. Then what we did, so from our team in IBM Research, we kind of reaffirmed our trust on transformers. So we published something called PatchTST. It came in ICLR, a renowned conference in machine learning. And PatchTST proposed a very simple concept that I will explain. And it showed that PatchTST can perform better or similar to D-linear. And most of the time it's better in a variety of data sets. And also it can be trained as a foundation model, right? So the idea is that so all these prior transformer models like fed-former, auto-former, informer, pyrformer, they were using time series modeling for modeling. They were using every time point data, and they were feeding this every time point data to the model. But what it seems like in time series, the local information is kind of, if you pass every time point information to the model, you are passing too much information and too much data to the model. So, and in time series, if you have one particular time value at a particular time point, it's very easy to predict the other time point in other values in the surrounding time points. Let's say I am collecting a data at 10-second interval. So the current data value, whatever I have in my, let's say in my heart rate, it probably be very similar to that after 10 seconds and before 10 seconds. So this very localized information in time series is not very much useful. And if I pass all this information to a transformer, it essentially loses and starts losing information after some time. And so what PatchTST suggested is very simple. You just patch the data. You just create small windows of the data. And for every window, you project every window into a using a perceptron layer, MLP layer, let's say, project into an embedding, and then pass those embeddings into the transformer encoder. So just by doing that, it's able to capture more like slow varying or more kind of better semantic information. And you can see from the results that it was beating D-linear and all the other transformer-based model. So this PatchTST is already available online, open source for your use. Then very recently, we have also, from our team, we have also proposed something called PatchTS Mixer. And here we have shown that patching is very important. So we are also patching the data. But instead of transformer, we are completely replacing transformer with a model called mixer model, MLP mixer model. So the entire transformer backbone is replaced with a MLP mixer block, where you can almost achieve similar performance or better performance in most of the cases than PatchTST, D-linear, and other prior models. You can see most of the bolts are here. So improvement over other models is huge. Let's say 23%, 30%, 64%. But improvement over PatchTST for time is for performance is only 1%. 1% is also significant for this type of applications. But what is more important is its lightweight and faster architecture. So because it's only MLP, so it doesn't have this complicated and more time-consuming self-attention layers. So that means it's very fast and it's very lightweight. So memory consumption in GPU is also way less. So if you read this patch TS mixer paper from IBM, you will see there is a time comparison as well with respect to transformers. So it's a very fast, which can be deployed in systems with low memory and achieving better or similar performance than patch TST. Okay. So we'll have a quick hands-on session now. So I hope my Visual Studio is visible. So
Yes, sir. It
what?
is.
Yes, thank you. Yeah. So what I'm doing is I'm taking this ETT data, which is electrical transformer data, which is also publicly available. Just search for ETT data in GitHub. You will get this ET dataset report. And so I'm showing. Yeah, I'm showing which I already ran. So I don't want to run it now because of time. So you can see it's already ran with this green tick. And so what I'm doing here is that initially I am importing Torch, importing Pandas, and all the things. And then I'm setting a seed. So this seed I'm setting just to, so that my, this is for a particular random seed. That means my result that I'm getting will be deterministic. It will not change every time. Because in SGD, you initialize your parameters randomly, then you follow the update procedure. So if you don't set this seed, every time you will run, you will get different results. Right. So now I am loading the data and I'm showing the data frame here. And you can see that this you have already seen, right? So it has 17,000 rows and 7 different columns. Okay, so the main important part for writing a time series model or any model in PyTorch is to write the data loader, because models are nowadays generally already available. So you can get any model from their open source code if you follow the paper and go to their repository. But the most important part is the data loader. So what we will do, we'll just go through the data loader once. So generally for data loader, so there is a tutorial in PyTorch called, just search PyTorch tutorial on data set and data loader. So it will come. So generally there is a class in utils data from where you import this data set. And then you try to create your own class inherited from this class, dataset class. And then you need to write two functions mainly, get item function and length function. So these two functions are mandatory functions to write a dataset class. So what we also write this read data just to read the data from file and create different splits of the data. Let's say I read the entire data, which is the entire pandas data frame. Then I want to create different splits. Let's say in the training part, I want to use the first 3 months of data. That means 90 days for my training. So first 3 months for training. Then let's say 8 days for validation, and then 8 days for testing. So in time series, we generally do not mix the training and validation in temporal manner. We want to keep them in sequence. So that's why it's called temporal cross-validation. So you keep the chronological order. You use first 3 months for training, then 1 month for validation, then 1 month for testing. Because when in the actual deployment scenario, you will never get something from the past. You will always get something from the future, the actual client data or user data or industry data. Everything will be in the future. So when you do cross-validation, you always try to maintain the chronological order. Otherwise, your cross-validation results will be very good, but actual test result might be very bad. So we do this thing here, and then we kind of create the training data, test data, and validation data. So in the get item function, you have to write how given a index, let's say index 0, index 1, index 2, how one sample you will throw out. And length will say what is the total length of your data set. So what we are doing here is we are just creating multiple windows. So if I have a time series of length, let's say length 100, we want to create multiple XY pairs. So we want to create a pair of XY pair of 10 length 10 and length 5, like that. And we want to shift it gradually over the entire time series. So my XY pairs is becoming, X means history, Y means future. Because we want to train the model as a forecasting, our input will be history, which is X, and our output will be future. So these windows are created here, you can see. So from S begin to S end, we create data X. From R begin to R end, we create data Y. Right. Then we return this X and Y. So my length, what I set here, my context length is 32. So given 32, I think it's hourly data. So 32 hours of history, we want to predict 4 hours in the future. So my forecast horizon is 4. So this data loader, this data set will keep creating samples in this shape, right? So I printed one sample here. So you can see its size is 32.7, which is X, and Y is 4x7. It has 7 channels. So all my samples will look like this. Given this 32x7 matrix, I have to predict this 4x7 matrix. So this is very important to understand, and also for coding, this is very important, how you set your data set. Then you pass the data set into something called data loader, which also you load from torch.utilsdata. And here you can set your batch size, whether you want to shuffle the data or not, etc. So this data loader, if you plot, let's say I plot one particular batch of the data loader just to see, right? So you can see the shape is 3-dimensional now. So batch size 128. So 128 samples, each of this size 32x7. Similar for Y. Right. Okay, now I create a very simple model. So for good results, you have to use some of the state-of-the-art models that we have seen. Just a minute, sorry. So this one is just a linear, it has like multiple linear models with ReLU in between. And what we do, this is little bit similar to the MLP mixer model, patch mixer model that in the last model we have seen. So it takes the data, it applies one linear layer, then applies activation, then it takes it permutes the data. So it takes let's say it first applies a linear layer on the channel dimension. Then it permutes the data and brings the time length dimension on the last dimension, and then applies the linear model again. So this is similar to the mixer model. And then you can see this training and testing loops. And these are very easily available codes in PyTorch tutorial. This part of the code you can get from PyTorch, any PyTorch tutorial websites. So you just replace the model with your model, the loss function with your loss function, right? And the optimizer with your optimizer. So in our case, the model is the model that I prepared here, the forecast model. And the loss function is mean squared error loss. And my optimizer, I'm using Adam optimizer. Then I have my training loop. I run for a few epochs. I do training. First, I do validation. I want to see my validation loss. And based on my validation loss, I can early stop my training if I want. Then finally, I test. So you can see that I plotted one example. So this is not a very strong model. This is just a very simple model. The forecast will not be very good, but at least you can see that it's able to get the trend that it's going up. So this is the forecast value and this is the actual true value. But if you use state-of-the-art models, you will see very good forecasting, much better than this one. Okay, I think this is the end of the demo. So let me go back to this. Yeah, I think this is the end of the demo. So so Sujata, we can go for the quiz then.
Yeah, we'll do that. So
Yes.
thank you, Mr. Arindam. Meanwhile, students, participants who are all there, see, this is a brilliant opportunity. Not every day we get such a key resource from company like IBM coming and giving us his valuable knowledge, his insights into a cutting edge technology and all that. So make best use of this session. There are ways and means by which you can ask your questions. I did mention it in the beginning of the session. Write your mail. Kishore, can you please post that mail ID once again in the chat box? Write your questions to the mail ID that I have been prompting through the session. Or you can meanwhile raise your hands and also get unmuted. I don't mind opening the chat box, but again, it depends on whether we have other distractions happening in the chat box. So I'm little hesitant in doing that. So thank you, sir. Thank you, Mr. Arindam, for a very insightful and informative session on AI and IoT. I think your session has provided valuable insights into this new technology. And I think, you did very well on engaging with participants by posting those questions time and again. I think it did keep them engaged. So we have the Q&A segment now and also the quiz that is going to happen. So are there anybody who's raising the hand so far? No. Any questions anybody wants to ask? So there was one question from Abhirami from Nanda Engineering College, Mr. Arindam. She says she can't understand the time series example. So she's asking you to explain it with another clear example, if possible.
So I'm not entirely sure which slide. Maybe it was very early in the talk, or if you are available, can you please write like which slide it may be?
Yeah, Abhirami. So I'm asking Sri Abhirami to unmute. Abhirami, if you're able there, you can unmute and ask your question.
Yeah.
Go ahead, Abhirami. Abhirami, you're unmuted. You can speak now. Okay, so we'll wait for her to come back. Meanwhile, you can stop your sharing your screen, sir. I will share my screen now.
Yes, sure. Yeah.
So if you have all, if you have all logged in into Slido, I'm going to give you exactly 30 seconds. We have been posting the Slido link from the very beginning of the session. So hopefully many of you have already logged in and you're ready. So how this Slido quiz works is you don't have to be staying in the Zoom screen. If you have logged in using a browser, any browser, it will work. Just stay in the browser screen only. All responses will have to be given in the browser. The Zoom sharing is only for the speakers and other champions to view the results, basically. Okay, I'm going to start the quiz. This quiz is basically a timed quiz, 20 seconds for each of the questions. There are only a few questions that from the whatever speaker has given. Rest of the other questions will be given to you later at the end of the series. Now, the first question is here for you. It will be shown on your browser. So stay on your browser. Which of the following is the common language for artificial intelligence? 20 seconds. Okay, so I do see that 90% of you have chosen Python. And the right answer is, yes, it is Python. So this was not a question from the speaker. This was a question that I have added just to make you people get used to the platform that we are administering this quiz on. We don't want the students or participants to actually miss the quiz, the actual questions from the speaker. So I introduced just a trivia type of a question. Another practice question for all of you. Here it comes. Okay, and the right answer is option C. 71% of you have got it right. So 424 people on 500 odd people who have registered for the quiz are taking the quiz. So rest of the 100 people also, please buck up, ensure that you participate. We had close to 900,000 people marking your attendance in the session. So I really don't know where the other 500, why they have not registered into the quiz. I would like to reiterate here that we are actually monitoring your attendance, participation in the Slido quiz, and then participation in the entire session of the series to give you a certificate. So if you have not logged in into Slido, you still have not lost time. Kindly log into it and take your quiz. Now the actual quiz questions are going to be shown on your screen. The third question. Okay, the responses are split here. And the correct answer is 32% of you have got it right. It is daily. Moving on to the fourth or the second question from the speaker. Option A is the most chosen option, and that is right. Good. Next question, 20 seconds. I do remember hearing about this in the session. Okay, but still we seem to have a split in the response. And the right answer is all of the above can be used. Following or neural networks can be used for forecasting. The next one. correct answer here is time series decomposition, option A. 39% of you have got it right. And the last question for the series session today. Split response, literally 50-50%. False is the right answer. So those are the questions that we had. So what you can do is come back to your Zoom screen and take a look at the score leaderboard here. Malati, Vishnu, Sheikh, Ismail, Jiva, Karthik. I don't know from which college all of you are from. All of you have got all the answers right. Well done. But Malati stays top on the leaderboard because of the fastest time frame in which she has completed. So in 1 minute, 34 seconds, she has been able to answer all the 7 questions correctly. Well done. Good luck to all of you. So I'll stop sharing my screen. So Arindam, you have anything to say on the quiz response? Are you okay, happy with the response?
Yes, I'm really happy with the response, and I'm excited to see that most of the people have. I'm happy to see that most of the people have understood the basic concepts which are kind of in the questions. Yeah.
Okay, so there is one question from Nitin of Tyagarajar College of Engineering, Madurai. His question is, he is developing a facial recognition tool. So he is using CNN LSTM for this. Can you provide details on how to manage sets and make the app more accurate? Is there anything that you can help him with?
Yeah. So by accurate, if you mean your accuracy of your model on the test data or validation data is not that high, then I would suggest to, instead of using some handcrafted model which you create by your own, it's probably better to read some recent literature, that means recent papers or recent innovations, some blogs, because people have worked for many years to develop more sophisticated models, which kind of takes care of the many problems that when we handcraft a model, we introduce many problems and bugs. So if you use a existing model or try to code the existing model yourself by reading the paper, that might give you better accuracy.
So I'd like it to be my own working so that I can get it patented and stuff, like unique work,
Okay. Oh, okay, I see. So you are saying it's a new model that you are building.
Yes, sir.
Okay, I see. So in that case, one idea is that you can try to at least read some of the latest papers to get concepts, like what new concepts are there to which kind of gets more accuracy in this type of domain. Then try to build something new on top of that. So that is kind of something incremental research, what we say, that you can do. Yeah.
Okay, so thank you, sir.
Yeah. So because I don't know the exact what problems, this needs deeper discussion, right? So yeah.
Any other
questions? Yeah.
Can you provide us with the previously done project code to understand? Sheikh Amin, you may have to unmute. See, I've made this option open. I think with all discipline, if we are able to unmute raise your hand, I'll allow you to get unmuted. Sheikh, you want to unmute and ask this question?
Raise hand, is it?
Yeah, you're audible. Go ahead.
Yes.
Sir, can you provide us the previously project code?
Yes. So by project code, you mean the notebook that I showed, right?
Yes, sir.
So yes. So the thing is that from IBM, we are open sourcing this. The patch TST model is already open source, and the TS Mixer model, which is the latest model, patch TS Mixer from IBM, we are also in the process of open sourcing that model with Hugging Face. So if you have heard of, there is a website called Hugging Face, which is basically a repository for all models and data. So we'll be open sourcing all these models and notebooks also we are planning to open source. So it will be very soon, I hope. So then just stay tuned to Hugging Face and our IBM research websites. It will be open source very soon. So then you will have access to all of these things.
Okay, thank you, sir.
Yes. But the patch TST model is already open source. So if you search patch TST and GitHub, there will be examples that you can also try. Yeah.
Yes,
Any other questions?
Mr. Arindram, one
Yes.
application that caught my eye, in the one of your beginning slides where you said where IoT is used. One of the examples you gave was smart traffic, and I thought that that's something relatable because most of us face it, right? You get caught at a signal if you jump the line automatically nowadays. The challan comes to your IDs. I was just thinking, how does IoT? Can you give us a little bit more explanation how IoT and AI plays a role there in smart traffic?
So it can be, it can be in different ways. Let's say it's basically a sensor, motion sensor that captures that can capture the speed of the vehicle. So generally for automatic vehicle speed monitoring, there are motion sensors that are installed in different locations that can capture if you in some of the automatic in some of the signals, if you see those are installed, right? And there are also multiple things. I mean, there are little bit futuristic things are, I mean, probably, let's say, sensors that are applied in your car to detect moving objects. So that is something also related to traffic, but it can detect moving objects and moving people. Those are again using sensors or camera. So these are all essentially collecting data all the time, and some kind of either edge computation or cloud computation is happening there. So in this way, I think, yeah.
Okay, interesting.
Yeah.
So there was one question from Babu Vishwa from Licit, that he says he's developing an AI governed railway track inspection device through which I can do a interface. That is his question. Is this question understandable? Because I don't see he has an audio. Babu Vishwa, I don't see that you'll be able to speak because you have not connected.
Yes, the chat it is given again, I think.
Yeah. AI governed railway track inspection device. Yeah, if you can explain maybe in chat also, like little bit more your question, it will be helpful to answer.
And Nitish, I don't understand your question also on multi-perceptron.
Okay, I understood his question, Nitish. So yeah, you can use other activation functions as well instead of ReLU. For example, you can use TAN-H. There is another activation function you can use. But empirically, people have found ReLU is enough to get similar performance than other activation functions. Probably ReLU gives better performance than TAN-H. But there are other, let's say, more advanced version of ReLU, like JLU and those functions. Those you can also use. ReLU is the simplest, so that's why I was showing that in my example.
Ajay, Ananda Soumya, any questions? You have all unmuted. You have any questions to ask? Go ahead. Okay, so if there are any more questions, we still have Kirtana, go ahead. Okay, so we still have 2 more sessions in the series. So if there are any questions, continue to write your questions in to the mail ID that we have been prompting. So we will get these queries answered through either Mr. Arindam or through the other speakers who are going to be coming for the next sessions. I would now request Dr. Kelita Cherian to conclude the session for the day. Dr. Kelita?
Yes. Yeah. All right. So looks like AI, ML, and IoT is an interesting topic. From our questions, we are able to see, most of the students are already doing some work in this area, building their own models. So I think it was a very apt topic and session that we had today. And it was a very good session in terms of you introduced us with to the industry 4.0. You led us through the brief on IoT sensors and how AI data and IoT task can be done on IoT sensor data. And then you walked us through other cutting edge technologies like, deep learning models, multivariate forecasting, time series, and the predictive maintenance models. And also showed us a case study. In fact, when you showed us, about things that the IBM research team has already developed, I think that was very interesting information to see, because otherwise we only get to read about some of these research data or research papers, right? We do not know what is happening within the industry. And from your talk, we were able to get that live view today, and right up to the hands-on session where you walked us through, those exercises. So I'm sure that everyone attending it has found it to be highly valuable and useful, the time that they have attended, spent here. So I want to thank you once again, Mr. Arindam, for sharing your knowledge as well as your expertise with all our students from PALS Partner Institute.
1 second, Kelita, I'll mute everybody for a moment. Yeah. Now you can unmute Kelita and Mr. Arindam.
Yes.
I've unmuted everybody.
Okay.
Yes. I think, yeah. Go ahead. Yeah.
No, I was just saying, so once again, thank you for sharing your time, your knowledge, and your expertise with all the students and faculty of PALS partner institutions on this forum today.
Yes, thank you so much. I want to thank you. Thank the PALS team, the entire PALS team, and also Kamal and the other folks from IBM Research for giving me this opportunity to kind of take this session. And I really enjoyed the session, and I really appreciate what PALS is doing. It kind of helps because there is a need. There needs to be someone who kind of connects this industry to the universities, and I think PALS is doing an excellent job there. So I really enjoyed the session, and I'm pretty happy with the results. So I'm pretty happy that people have understood at least some of the basic concepts I wanted to share. Yeah, it was a great session. Thank you so much.
Thank you, sir. So we have more than 1,000 people who have participated, though the Zoom screen and the live session did not show that the actual numbers. I do understand that some of these colleges are screening it in their auditorium. So, they are using one login, but then, there is a bunch of 100 odd students sitting there and watching the session. So I think your reach has been over 1,000 participants today.
Okay, that's great. Thank you so much. I hope I have shared this AI for IoT things to the students.
So
Wonderful,
one
sir.
last question, since this is a very current topic within the industry, if students want to pursue this as a career path, most of them are AI, ML, and computer science students, what are the sort of skills that they need to develop? And how do they get into industry, or how do they get even into an IBM research labs if they want to pursue that as a future career path?
Yes. So I think this is becoming extremely important. So as skill set, so I would say you should try to take even if you are in undergrad or if you are in masters, first try to take the basic machine learning courses like pattern recognition and basic machine learning. So most of the time what people are doing nowadays is they don't take the basic courses and then they directly take the deep learning courses. So unless you do not understand what is cross validation, what is a loss function, what is a model weight, it's very hard to understand and grasp the deep learning. So I would ask to take machine learning courses, the basic ones, then probably deep learning courses and optimization courses, then definitely build skills for Python and PyTorch, at least one of the deep learning library like PyTorch or TensorFlow. This is something is extremely important.
So I hope our students have noted this, and over the course of your academic progression that you will try to gain knowledge and all of these skill sets so that you're ready by the time you come to your 4th year for placements and jobs in the industry. Thank you very much once again for this session.
Thank you. Kishore,
Thank
you
you.
can stop the streaming and recording, Kishore. So participants, we have posted the feedback link. Take few more minutes and share your feedback. We will be passing on the feedback to the IBM team so that the next week, we do have